Hello everyone. In this lecture we're going to be discussing about Bellman-Ford algorithm for finding single source or single source shortest path in a graph. So let's talk about single source shortest path problem. We have been given a graph and we like to find a shortest path from a given source vertex to each other vertex in the graph. Or you may say that, let's say we have been given a source vertex S and we have been given this directed uh, edge directed graph with some weight on each of the edge, okay, and weight can be negative. In other words, we have some function, weight function, okay, for each edge, okay, which is mapping to some real number. Now, you may also think about a practical problem. Let's say you want to visit or you want to take a road trip from Toronto to New York, and there are different cities on the way, and you want to find what would be the shortest path to each of the city from Toronto, so that you can visit each city on the way while you are driving from Toronto to New York. And you can construct a graph, okay, and weight on each path or each each edge in the graph. You can think of either the distance or either, let's say, the delay, how much time is going to take from one city to another city, and you can convert that problem into a single source shortest path problem and apply Bellman-Ford's algorithm. So essentially what we want to know is that we have from the source vertex a shortest path to each of the vertex in the graph. So that's essentially we want to know. So let's say how we can apply Bellman-Ford's algorithm. So what Bellman-Ford's algorithm says that it will return true if the graph contains no cycle, no negative weight cycle from the source vertex, and if it finds no cycle, then it will give a shortest path from source vertex to each other vertex in the graph. And if it finds a cycle, then it will just say false, or it will not give you the path. So let's say what this algorithm says. Simply, the step first is a initialize subroutine, which is initialization step. This is very similar to what we learned in the previous lectures, that okay, we're gonna put some values onto each node in the graph, or some sort of way to initialize the value or on each some key value on each node in the graph or each vertex in the graph. So some initialization process, and then um, from step number 2 to 4, so it takes the takes the node, it starts from the source vertex, which is source vertex is identified or given, and proceeds forward. It's very similar to Prim's algorithm, what we learned in the previous lecture. So very similar to that one. Now the relaxation procedure, this is a another subroutine and something new, where it relaxes the edge, okay, edge in the graph. The idea here is to find or to relax the edge, means that if we find some other route from U to V which has lower cost, then we change the parent of the v, okay, to the new parent u. All right, so it's some sort of way to adjusting the minimum cost route. And the line number 5 to 7 are just simply checking whether there is any cycle or not, and if there is no cycle, the algorithm will give you the shortest path. All right, so let's say what is initialization subroutine says. So it's very simple. For each vertex, v dot d is nothing but some sort of distance or key value, whatever you may like to think of. Initially, we don't know how far that node is from the source node, so we just put some high value or infinity, and we make the parent of the vertex. Each vertex is null because we don't know what is the parent of that node. Okay, and we initialize the s dot d, means the source vertex distance is 0. Okay, that's the initialization step. And what relaxation step says that for each edge, it relaxes the edge, or as we discussed earlier, that trying to find some other alternative route which has lower cost. So as you can see here with this if condition, if the v dot d, okay, if we are taking the edge between u to v, and if the v dot d marked is greater than u dot d plus weight on the edge uv, then we just simply update the new distance and the new parent of the v. As simple as that. Or we can pictorially see that. Let's say earlier we had the distance of v9, okay, and we found that okay, we have another possibility that the distance is lower. Okay, so let's say 4 plus 3 is equal to 7, lower. So we just simply change the parent of v to u and the new distance, which is 7. So that means we relax. That procedure is called relax. Now naming convention is simply as per your textbook, Thomas's Corman textbook, so that you guys don't have any much confusion there. So I just kept the name same. Okay, so let's try to implement or see pictorially how this algorithm works on our sample graph, right? So sample graph, let's say this graph is being given, and we have source vertex and weight on each edge, and directed graph is given. So how the algorithm is going to implement? So initialization is step. We initialize source vertex to 0 value, v dot j is 0, and infinity on each other vertices. Okay, that's the initialization step. After the initialization step, for each vertex other than source vertex, okay, so for each vertex starting from the source vertex, we implement line number 3 to 4. What it means simply that if we take the vertex s, we selected it. Now there is the edge between s to t, and t. So what would be the distance between s to t is 5, and s to z would be 6. Okay. And now if, say for example, next we take the vertex g. So what are the possibilities, possible edges from the z? One edge is between g and x, another edge is between g and y. Okay, So only two edges are going out. Now if we take the edge between g and x, so what would be the x dot t? It will be simply 6 plus minus 3. So that will be 6 minus 3, okay, and equal to 3. And what would be the weight on what would be the y dot d? Simply 9 plus 6, 15. Good. Now we move on to the next vertex. Next vertex is, say, t. Now here it's interesting to note that we have three edges going out from t. Okay, so let's say t and g. If we take this edge, then we're gonna see how the relax procedure is working. So what it says that, okay, what is the weight on z, or v dot d, or z dot d is 6. Okay, 6 is less than 7 plus 5, that means 12. So we don't touch it because we already have the lower v dot d here. Okay, now let's take the next edge between t and y. All right, so between t and y, if we try to relax that edge, then what's going to happen? Because y earlier was 15, 9 plus 6. And now the new y would be 5 minus 4 equal to 1. So one value is less than what we had earlier, 15. So we change, or we update the parent of y. Parent of y would be t, and we remove or we just updated the parent. So old parent of the y was z, which will no more be there. Okay, now let's say next vertex. So if we say next vertex is x, so what it means that we simply relax the edge between x and t, and we get the new value of t dot d equal to 2, and new parent of t would be x. Simply, an old parent of t, which was from s, is gone now because we did relax the edge between x and t. Okay, so it simply says that, but we keep on that we updated new parent and new t dot d. Same way we can apply to the relaxation procedure on node y. Okay, so this way, in this example, this Bellman-Ford algorithm will return true, and it finds the shortest path from the source vertex to each other vertex given by this blue glow lines. Okay, now let's talk about complexity of this algorithm. Say simply initialization step would take just O1 time. Okay, and the initialization step would take O of v time, because here we have the for loop, and O of v time. And then if we see the for loop from line number 2 to 4 or 3 to 4, that will take O of e, okay, for each edge, for loop at line number 3 and 4, and for loop at line number 4, O of e. And since we have another upper loop at line number 2, so we can say the total or overall asymptotic complexity of this algorithm as in the order of v multiplied by e, where v are the number of vertices and e are the number of edges in the graph. All right. So thank you guys. Thank you for liking and subscribing the Professor channel on YouTube. Hope you have enjoyed this lecture. Those who have not subscribed, please do subscribe. We appreciate your support and feedback. Have a wonderful day.